Anyway, pretty much all of the programming languages that exist in the wild today have the same strength in the meaning that they can, that the programs making them can compute the same things. And mostly all of those differences between those programming languages is what is the style they chose to do it in. There's this, we could try to perhaps classify a bit of the space of programming languages. So we can try to describe like what are the major paradigms and how they interact. So, well, from the point of perspective of Grasshopper, this is actually really interesting that most programming languages and most of the old programming languages actually are textual, but that could possibly change in the future. So text isn't actually the best way, or at least not the most comfortable way to actually input a program. The text gives you way too much freedom, and then there's a lot of maintenance that has to go in to actually parse the text into the semantic meaning of the program when the compiler tries to interpret what the program is supposed to do. So
we should maybe also mention or explain what the compiler is.
Yes, unfortunately, this is actually like a really fuzzy topic as well. So, okay, one of the many lines you can draw when you're classifying programming languages is whether they are compiled or interpreted. And this is actually a very fuzzy line. A compiler is something that translates the text that you write, that is the text of your program, into a program that your machine can run. However, so this is certainly true for interpreted, for compiled programming languages. But actually, interpreted programming languages also have in them a sort of a mini compiler that transforms the text that you write into some intermediate form that then it interprets. So this distinction isn't actually so easy to make. But in general, an interpreted programming language is something that you don't necessarily see the explicit step of having to translate the text into something your machine can run, and it's just the step is bundled in this single process of running your program, and it is translated on demand, pretty much transparent to you. While for compiled programming languages, you have to explicitly translate the code and then you can run it. But as time progresses, this definition is pretty much more and more blurred, and every interpreter has a compiler inside, and many compilers currently have interpreters inside for some, I don't know, compile time metaprogramming stuff. So
I think it's an interesting notion that people that I keep thinking about, that the code that you write as a human is not the code that the machine is actually reading. So there is always something in between of you and the computer and the machine that needs to translate from your language to the machine language. And just bringing this to a different realm, a different domain. When we speak about architecture, what is happening right now is that the notation of the design of the project is changing a lot. And before, the drawings, the blueprints were made by people for people. So a designer, an architect was drawing something that is a simplification or a notation, some sort of record of the idea that should be easy to read by another human being. Now, this is changing a lot as well, because less and less human beings are producing the results, and more machines are. And we are somehow in a bad moment in time when we as designers very often still need to make the blueprints for people, and some other person then takes the blueprint made by the designer and somehow translates it to the language of the machine. And I think very soon, and this is actually happening for us already, we might forget the human-to-human notation, because we are using now software and machines to actually produce the design, and that machine already has all the necessary information about the design. We can completely skip the blueprints that are readable by human beings, and we can directly translate that to something that a machine can produce. This being said, that doesn't mean that there is no evaluation by humans, and I think that applies to the code as well. We just don't have to create a technical version of the notation. We can think of better ways how to present the content to other human beings. And this is something that is happening in the code as well. When we were working on the Urban Selector project, we took the review process, where I made a code and you went through the code and you were trying to understand what I was trying to do and made a review. And this is still the notation that is good for human beings, and then it's translated to the machine. But also that code was full of comments, full of stuff that the machine doesn't need. And that, for me, it's an analogy for some sort of, I don't know, in architecture, it would be a rendering or a virtual reality or any sort of picture animation. You cannot actually produce the thing out of that notation, but it's good for other people for evaluation, and it's more focused on this purpose rather than just looking at blueprints, because that's what architects still do. They take the technical drawings and evaluate as people, and we don't have to take the technical, the compiled, the translated version, and we can focus more on how to actually present the content in the most natural way for the presenter. Mm-hmm. Maybe we can. Yeah.
Sorry. So would you say that in the earlier process, when there was this another person, this middleman that translated the blueprint for the machine, would you say that there's actually some information lost in that translation because of the person-to-person process?
It happens to us this week while we are presenting. I don't know if I have it in my reach, but yeah, it's on a different table. I will show you later on. We have no, I will show you right now. I'll just bring it.
Oh no, what have I caused?
Yeah, this is some sort of an improvisation, but I just want to show you. I've got this wire. This is just a metal wire, and we needed this to be actually produced by a machine in a very precise way. So this has certain shape. It should perform. It should actually serve certain purpose, and all the parts they have their angles and dimensions and everything. So I made a 3D model of this in Rhino, and at that point I called to a company asking them whether they can produce something like that and what sort of data their machine needs. And they told me, sure, just send us some PDF with annotations and dimensions. And I was like, no, that's not really perfect, because I already have the digital model, and your machine is digital, and your machine will bend the wire just digitally, and just tell me what data your machine actually takes. And they told me, we've got a person there standing on the machine, and the person just has a tape measure, and we just need a prototype, and we will feed the machine the data. And the thing is, eventually they never needed the digital data from me, and it's still happening. So I made a lot of annotations. I put all the dimensions there and everything. And I believe that I made it very precisely. And eventually all the measurements fit, except one, which is here. And that one is almost twice as big as it was supposed to be. So if you're asking me whether there is some information loss, yes, always. And surprisingly, everything else is perfectly according to the assignment, even the angles, everything. Like, I'm very surprised that they managed to translate, but they had the blueprints made by a human being, which is me, and another human being was reading that and feeding the machine. And I believe that we would completely avoid this error if they were able to use the digital data. That's what we do with most of our suppliers. We know what machines they are using, and we are somehow, oh, I actually broke it. Good to know that it can break. Anyway, so our other suppliers, we know what machines they use and how, and we are trying to produce data especially for them. And for us, it's also a lot of, it's time saving, because making the dimensions and annotations, in other words, to make a documentation and notation precise and informative enough so that a human being can read all the information there, it's an extra work. You need to add extra annotations. And you do that also in the code when you add comments and so on. So this is a waste of time and a waste of information for us. And it would be amazing if we could just feed that digital data to the machine. But still, if we want people to evaluate, we create different notation of what we are doing.
Yeah, exactly. So even in programming, if you're just having a conversation with the machine doesn't really care about your particular style of programming that much. It just takes in the meaning, and that's enough. But once programmers collaborate, then some kind of communication language needs to be established. Otherwise, it's just too much effort to try to understand what the other programmer did. So they have to meet somewhere halfway, ideally.
I know that there is some sort of exotic way of writing code when you're basically creating some sort of a website or some sort of a text file that is basically in an artistic way describing what you're doing. You're basically writing an essay, and you've got quotations there, and you say, in the next block, I will try to achieve that with my code, and the code would be something like this, and there's quotations, and you've got the code there. And this creates both the human readable version of the code, and also the machine just completely skips your essay and only reads the quotations and tries to compile that. Is that something that you think is a good idea, or is it just too strange?
Yeah, that thing I think is called literary programming, and I've seen it in certain places. So actually, the idea is quite old. I think comes from the 70s or so. It's really interesting, and I believe it could be a good idea. It's just that perhaps human language or the natural language just isn't precise enough to define those things. So, and actually, once you desugar it, the process is that the tool that builds your code actually just extracts the code itself and discards the rest. So this doesn't actually force you, this doesn't force the documentation and code to be in sync in any way. I think it's a really interesting experiment. I personally don't use it and probably wouldn't. But when I first found out it exists, it actually fascinated me for some time. That this is also a way that people do it, and some people really do this. And if the personal style of the programmer really fits this well, and there's only one programmer, then perhaps the program itself can be a form of, well, maybe not art, but good craftsmanship for certain.
I'm sorry, I took you away from the distinction between compiled and interpreted. Can we really briefly come back to it, and then we'll move on?
Yeah, sure. So pretty much the distinction is that you can run a program in the interpreted language pretty much out of the box. You need to have some kind of tool installed. This is usually called the interpreter. And it ingests your code, internally translates it, and then evaluates it on the machine that you're running. For the compiler does a similar thing, but actually instead of evaluating the code directly, it just outputs code that your operating system and your processor architecture directly can run.
So in other words, the compiled code is being translated for the machine, and the machine is trying to read something that the programmer wrote directly. And I think we can also talk about the implications. Does it mean that the interpreted programming languages, you can somehow do the live coding or something like that? Is that one of the good things?
Yeah, for sure. So many of the so-called dynamic programming languages today have this thing that's called a read eval print loop, where you just pretty much have a conversation with the interpreter. You tell it to do things and it directly does them, prints back the results for you. So this can be really useful for some kind of prototyping or just running isolated snippets of code.
Can we give an example of a compiled and interpreted programming language, and for what purpose is it used?
Mm-hmm. Yeah, so a very good example of a compiled programming language would be C. C is thought of as a, well, historically thought of as a high-level programming language, because back at those days, assembly was the low-level programming language.
Have we spoken about this distinction of low-level, high-level?
Okay. We haven't yet, and we can, but this also isn't.
Let's just make it very quick, if I may. Low level means how close you are to the metal. So if you're programming the electrical circuits in your computer or any sort of device, that's very low level. High level would be that you write something that is very similar to your to natural human language, and it has to be translated through all the layers all the way to the metal. So that's the distinction between high level and low level.
Yeah, exactly. And in high level, you usually don't care much about what kind of machine you're running on at all. Sometimes this is a very good thing because it allows more people to program, to, I don't know, make art. But also it kind of takes capabilities away from you, but somehow most of the people actually don't need those capabilities. So it's
also you cannot do optimizations. So low-level programming usually results in very, very fast running programs, as fast as the hardware allows you.
Yes, because it gives you control.
Yeah, let's go back to C and something else. Like C is a high-level programming language, which nowadays would probably be considered a low level, right, in comparison with the new languages that are much more high level, and it's compiled, right?
Yes, the things you would usually write in C are operating systems or GPU drivers or any kind of device drivers, actually.
Also, Arduino language, I think, is either C or C++ based. So you can also write code for microcontrollers and so on, which is very efficient.
So this actually may be a very important language for digital artists, because exactly C gives you that much control that you can run in a very constrained environment, such as a low-power device like Arduino, and actually still make something happen on those glacially slow processors. Also, C powers rockets, C powers airplanes. So everywhere where there's this energy constraint that you have, and there's a real-time component to the program. So the airplane controller has to do something, I don't know, at some frequency, no matter what. The computation just cannot take longer, or there could be consequences.
And very often, you can make a code that runs without an operating system, right? So it runs directly on the metal without having the layer of the operating system.
Yes, exactly. So when you are writing an operating system, there isn't one to start with. So you are the operating system.
What about the interpreted languages? Which one would you pick as an example?
Yeah, well, there's two very good ones. One, I would say Python, which is, I believe, used quite a lot in the artistic community as well.
It is.
So Python is a way of gluing things together. So usually you have tools and frameworks already done for you, and you write relatively short, and that could also mean thousands of lines of code. That's still relatively short programs that just glue together existing functionality to make your art, to make your product. And Python does make this really easy for you it tries to lower the cognitive burden on the programmer, so the programmer can focus more on the logic of the things itself. On the other hand, it gives you less control. So if for some reason things start getting slow, there's not that many options you can do to optimize. What you could do is, for instance, take some piece of the Python code and rewrite it in, let's say, C, and then just call that C from Python. The other very, very popular high-level programming language is JavaScript, which runs everywhere. There's, well, every browser runs JavaScript. There's server-side JavaScript as well.
We also have to say that people mostly think that JavaScript is a language for making the websites animated, but it's not true anymore at all.
Yeah, exactly. It actually used to be true, and it was its original purpose. And there's this rumor or legend that it was designed in 2 weeks. That's why it is like it is. Well, currently, what you can pretty much do anything in JavaScript, either directly or because you can write some low-level code in some other language and link that to your JavaScript program. So your JavaScript can actually call this low-level library. And similar to Python, JavaScript gives you a lot of comfort. Actually, there's a matter of taste difference between these two. So Python is a bit more strict in what it allows you to do to prevent some kind of programming mistakes, and JavaScript tries to make sense of everything, but usually it's maybe a bit like autocorrect, so it not always corrects your error to what you would like. Mm. So JavaScript programs usually do unexpected things when there's errors in them.
Before we are going to talk about different distinction between programming languages, and I think we should get there pretty soon. Let's discuss a little bit. Very often when people are starting or thinking what programming language should they learn, it's kind of a difficult question, and we can maybe discuss that a little bit more. And let's discuss it mainly from the viewpoint of artists and creative people who are not trying to become programmers, but they want to use coding to achieve their goals. And I would say there are some usual suspects. There are existing things like processing, or there is Grasshopper. There are some scripting languages for Unreal Engine, for Houdini, for the Unity engine. There is open frameworks, and there is a lot of different programming languages that seem to offer to achieve something. Can we somehow talk about the differences between them and how to choose the right one? Because I've got some sort of notion that I would like to say at the.
I know where you're heading.
You think? Because what I want to say is that you can use anything, because it's not because
that's what I wanted to say as well.
Yeah, but I knew. I would just give you like the spoiler. When you see some stuff on Facebook or social media, you see that somebody made something that is interactive and obviously coded and so on. People very often think about like, whoa, what is it made in? Like, what should I use to achieve the same thing? And very often people fall into the false idea that you need to use this thing to achieve that thing. Like, is it made in Python or is it made in JavaScript? Should I learn Python or JavaScript to do this? And I think the thing that people should understand is that you can use anything to achieve anything. It's just maybe somewhere there are ready-made libraries, or like yes, something is faster, something is slower, and so on. So
what I'd add to that is that usually the tool you use, the programming language or the game engine or the graphics library, it solves the easy things for you. And the hard things are what is the core of the thing that you're making. And no game engine solves that for you. No game engine solves the game logic, the idea of your game for you. You have to have that yourself. The game engine can give you really nice rendering, but it used to be the case, it's not so much anymore, that you could tell a game was made in a particular game engine because the rendering looked pretty similar. The input, the controls looked pretty similar.
And the features were out of the box.
And the features were out of the box, and it was just easier and perhaps cheaper to use those features.
Yes.
Which is actually a good point, that if you don't really have that much of a budget, it is really, it can be a really good idea to actually use one of these tools.
I think there is an interesting notion that Manuel said 2 days ago, and that's probably the story of many of us. He said that the first tools that generated the things for him, he made in processing, then he went to Unity, and now he uses pure Java. And we probably have to say that processing as a programming language, it is basically just a library it's basically just a Java library, or JavaScript library there, or even Python library. So basically processing, it is a programming language on its own, but in fact, it is still Java. And what you said, that it gives you the easy basic things to you out of the box, then it's good for prototyping, for achieving a certain simple goal very fast. But once you want to make something more complex, it doesn't help you, or it doesn't help you so much. So basically, you still need to build a robust structure and skeleton, and then you can use the little small easy things that all these engines or all these libraries give you. But still, when it comes to building up the skeleton, you need to do it on your own, the hard way, I would say.
Mm-hmm. Yeah, well, also if you go the hard way all the way, so if say you want to build all of your tools, then you perhaps spend too much time on building your tools and not enough times even thinking about what the core concepts are, what you're trying to build. So it really pays off to prototype, and to prototype in a thing that makes the easy things easier.
Now a super hard question, or the question is easy and the answer will be hard. For somebody who is a creative and has no experience with coding, they still need to learn how to write code in certain language. What is your recommendation? Where should they start? Which language should they pick as the first one to learn? Also, not to discourage people, also to achieve goals really fast, and so on.
So this is the part where I say Haskell. Or
oh, no, let's keep Haskell. Let's keep Haskell to the moment when we are talking about imperative and functional programming languages.
Okay, I would say pick one of the more forgiving ones, but also pick one of those that gives you really good feedback early on. Well, you have to somehow balance that. So too much negative feedback just discourages you, but too little feedback lets you do complex errors that are really difficult to debug. So on one hand would be JavaScript, which allows you to do pretty much anything, but it doesn't tell you that there's an error, and it just tries to run it and it does something, but you don't actually know what the thing is. I would say, well, it's been a while, but perhaps if I was just starting now, I would look into Python, because this is like a very, very good middle ground, that it tries to catch many errors early, but at the same time is very open to prototyping. And there's support for graphics libraries and stuff like that.
Some time ago, I was using processing a lot because I thought it's a good thing, a good place to start. The original processing is based on Java. I was briefly trying to use open frameworks, which is actually processing just based on C++, which makes it much faster and lets you achieve or be more ambitious when it comes to computation power. There was this boundary for me, and it was so difficult for me to even do the hello world, the simplest code that you can do in open frameworks, because I had to install so many things to make it work, that it was very discouraging. So and processing is easy because you just download that, run, it opens a window, and you just type code. Now I don't think it's that easy anymore. I think the problem is that it's somehow getting there is too much code that you need to write, which is unnecessary. So you need to learn so many things that probably are not so important for you to write the code. And therefore, my recommendation here would be also probably Python, but just pure vanilla Python might be a little bit discouraging because it doesn't give you visually pleasing results out of the box. So there is a Python version of processing, which is still not the best thing, because processing, still there is a lot of concepts that you need to learn extra, that the processing is not as simple as it tries to look like. So that's my problem with processing. It's not that it would be way too basic. No, it offers a lot, but it also demands more than I think is necessary. But still, as a good compromise, I think the Python version of processing seems like something that is a good starting point.
Yeah. Also, if you have a lot of time to invest, you could try to learn one of the game engines as well. So, for instance, Unity with the C# scripting is actually pretty simple to start with. But once again, you'll eventually run into the part where you need to start understanding things on first principles.
Yeah, we've got a question in the Zoom chat. Whether we are recommending learning Python inside or outside Grasshopper. That's another thing.
I think we'll get to there.
Yeah, we'll get to there. But just to answer, I would recommend spending some short time learning Python outside Grasshopper, and maybe using it with the processing Python would be a good thing, because it would give you results very fast, and there are examples and so on. The thing is that when you have any scripting inside of Grasshopper, or basically anywhere, but let's talk about Grasshopper. There's an option to write code in Python. There is an option to write code in basically any .NET language, which mostly means Visual Basic and C#. The thing is that they are equivalent, and this is that's what we've been talking about so far. That all these options are equivalent when it comes to the results that you can achieve. So you can do the same stuff no matter if you use Python, no matter if you use Visual Basic, no matter if you use C#, and mostly the logic would be very, very similar. You just would write the thing slightly differently, like using curly brackets or not, using something at the end of the line or not, and so on. So that would be the differences between these three. And also Visual Basic and C# in applications, they are so equivalent that it's just the way you write the line would look different, like different languages, but the sentences would be the same. So that being said, is that even if you are using Python inside of Grasshopper, you need to understand the logic of the code, no matter if it is in Grasshopper or not. So I think it's better to learn how to write code in general, even though it doesn't give you visually pleasing results. But then you will need that knowledge later on, or you can benefit on that. And that's why I said processing, Python version of processing, because that even gives you the visually pleasing results. Can we move on to the distinction between imperative and functional programming languages, at least slightly, just in terms that are easy to understand? Before we start, I want to say that so far even now I was saying that these three languages are so similar to each other that you can word to word translate them, and the logic would be the same, and the result would be the same. And we are actually saying that no matter what programming language you use, the results can be the same. But when it comes to the distinction between the imperative programming languages and functional, and even there are more distinctions like procedural, object-oriented, and so on. But let's talk about imperative and functional only. Mm-hmm. The way the code looks and the way the logic works is fundamentally different, and I think it's very important also for creative people to understand this difference, and we will come to that later on. Can we talk about this?
Yeah, let's try. I'd start with imperative, because for some reason that is what humans are wired better to understand initially.
And surprisingly, it's a newer concept. Also, what I would like to say, it seems like this distinction is like the functional programming languages, they were first, like even maybe before computers. Then imperative came, and now there is like a revival of the functional programming the old way, and it seems like the imperative is easier for people to understand. Anyway, let's
initially. Well, also we should mention that many of today's programming languages are a mix of those two in some amount. Okay, so in an imperative programming language, you can imagine that every line of code or every command that you type is an instruction for the computer to do something. So I don't know, I want to populate this memory with these values. I want to copy these values to some other memory. I want to draw something on the screen. And always you can imagine it as though it were a recipe that or an algorithm that the computer just goes through and does exactly what the recipe says. On the other hand, declarative or functional languages, the way that you write them is a bit different. And there the programming model or the thinking model is that you describe the properties of the result. You describe the properties of the process as well, but you don't specify exactly how the program should exactly do that. So for instance, there's this very, very commonly used example that you have some set of data or a list of items, and you want to filter them. You want to only some of the items to actually emerge from the list. So in a functional language, you would describe the condition, the filtering condition, which actually selects the items from the list, while in an imperative programming language, you would manually iterate over the memory and copy those items somewhere else based on the same condition. So in a way, functional programming languages are much closer to math. There's some connection to predicate logic. There's connection to lambda calculus. Yeah, and it's more about your intent, the logic of the program itself, and there's less management like computer, please do this and then do that. You just say, I want my result to look like this, and it has to satisfy these conditions.
That was very abstract. Maybe we can. No, that's fine. That's a necessary thing to do. Maybe we can name some of the famous programming languages that are functional, purely.
Okay, so a very famous functional one is well, it's a family of languages called Lisp. And there's there's many variants like Scheme and Common Lisp. Those used to be famous.
Also Clojure.
Also Clojure, which is a modern one which actually runs on the Java virtual machine. What they're famous for is in the, I think it was 60s or 70s, for machine learning research. And
we also have to say that machine learning is not a thing of 2020, but it was around in the 60s.
Oh, I'm sorry, I misspoke. I was supposed to say AI research.
Okay. Wow. But still, all these things, like, they are not new concepts.
Yeah, exactly. And also many of the computers in that age actually was hardware that directly interpreted the Lisp programming language. So in some Rocket code, they had a Lisp processor, and they could replace a part of the program to actually hot patch and hotfix the flight computer in the Rocket, which was pretty interesting. So Lisp has this really interesting notion that code and data is the same thing.
Maybe we can show, and you haven't mentioned Haskell.
And yeah, the other part of the functional programming language spectrum would be Haskell, which shares many of Lisp's features. So once again, it still is that it's more about you describing what the result should look like and less about actually telling the computer to do it. But where these two differs is types, or the ability to know the types before the program is run. So Haskell is based on a field of mathematics called category theory. Oh, okay, you just stopped screen sharing. Oh, I see.
I started screen sharing. I would like people to see actually how does the code look like. There is a very nice website called Rosetta Code, which is named after the Rosetta tablet board. And it actually shows several well-known algorithms written, or equivalent algorithms written in different programming languages. And this is the one that I like the most. It's a sorting algorithm called Quicksort. And we can have a very quick look. How does it look in, for example, C, which is a usual, like a very well-known imperative programming language. And you can, even if you cannot read the code, I will just tell you very quickly, each line means some sort of a command. It's like you say, okay, make A contain this, then do this, make N contain this formula, or the result of this formula, and then keep repeating this, and then do that, and which is defined here. And this says if something is something like that, then just go out, and if it's not, continue, and then keep repeating this, and gives commands to the computer. So this is what it looks like in C, the sorting algorithm. We can have a look. How does it look in Java, for example? It looks something like this. It's slightly shorter, but still there is a lot of commands for the computer. And you see that just like you said, some of the programming languages, they allow you to work in both paradigms, the imperative and functional, and Java is one of them. So this is the same algorithm when it's written as a list of imperative commands, and this is how it looks when it's written in a functional way. But the nicest thing that I like is the Haskell version of this, and the same algorithm in Haskell is basically this one line. And the reason is that it's basically just, but this is kind of a hack, I have to say. This doesn't apply for all the codes, but in this case it does. And the nice thing is that it basically, it tells you to take certain data and do some mathematical operation on that. And even the mathematical operation is described here. So it's not using some ready-made built-in function, but the mathematical description of the sorting algorithm is this simple and easy. Whereas when you need to write it in an imperative language, it's just a completely different story, and it's just way more difficult. We can say that Lisp, actually, as far as I know, the functional programming language group Lisp, the word Lisp means actually list processing. Is that correct?
I believe it has something to do with the word list.
Yeah, I think it's like list processing, which means that basically you take lists or like streams of data, and you apply certain functions, mathematical functions or different functions, to the data, and output new set of data and do something with that data, and so on. Mm-hmm. And you can imagine that this is incredibly useful when your program should actually process data. So that's useful for economy. So you input some economical data and you do all sorts of processing, and then there is the result. It's good for weather prediction and so on. It's not probably so good to operate an airplane, because there is a lot of imperative commands that you need to give to the airplane. I'm pretty sure it would be possible to write in a functional way, but probably that wouldn't be the best idea. But surprisingly, it seems like for most of the creative purposes, when you're not making a performative thing that should do something in real time and respond, if you're not doing that, if you really want a result to be some sort of static set of data, it is a good idea to use the functional programming. And you know where I'm heading, right?
Absolutely, absolutely.
I want to say let's go there. I want to say that this introduction that was very vague and somehow too theoretical, it leads us to the moment where I want to say that Grasshopper itself is a functional programming language. And it's a very beautiful one. And not only that, it's also a node-based visual programming language, functional programming language. So it's a combination of two really cool concepts where you don't have to type code and you can just draw the stuff. And also at the same time, you are processing lists in a functional way. And we can demonstrate that in a screencast. I will share my screen and show you what do the concepts actually mean. But we didn't discuss this before, but would you be up for some sort of a pair programming? Maybe if we could open some playground and try to do the same stuff, let's say in JavaScript in the functional way, or any language that you pick.
We can try it. This may end terribly, but we can
maybe
try.
But let's try to improvise. What I would like to do is maybe we can do both things at the same time. Like this is going to be some simple math that we are going to do, but we can try to write the same code in an imperative way, then in a functional way, and then in Grasshopper way. Okay, let's take a list of numbers and let's or just one list of numbers, and let's multiply the numbers by 1.5.
Okay.
Okay, so
the result is another list with the numbers.
Yes, and we are going to explain that idea. I don't know if we both can share the screen at the same time. I don't think so, actually. It would be awesome if that was possible.
When you share the screen, it just takes all of my screen.
Yeah. I will unshare and I will make you a co-host of this so that you can share your screen as well. Maybe, I don't know, is there any online tool where I could open the same code that you are running?
Well, we could use some kind of playground.
And you will send me the link and we can then, I can open the link. Okay.
Yes.
So let's just generate a series of numbers here in Grasshopper, and I will say I want to create 10 pieces of numbers like this. So they are going to be numbers from 0 to 9. And then I will do multiplication. And I will say I want to multiply the numbers by 1.5. And as a result, I will have another list of numbers that are 1.5 larger, each one of them, than the ones before. Now, I will, before you write the code, so are you making the imperative version first or the functional one?
I didn't start it, but I think I will start with the functional one.
Okay.
And then we'll.
Okay, so I will just explain several concepts here. This is super basic. I know everybody knows this, but I just want to speak about that in from the viewpoint of a computer like programming language. So what is basically happening here is that here I'm generating a series of numbers, which means that inside of this component, which some people call a command, some people call it a function, I would say it's some sort of a function. What it does, it takes basically no input except the number of outputs. So now it doesn't take input data. So from no data, it creates new data. And because this list is basically the data we care about, this is just a constant that defines a parameter that defines how the data should be created. So we created the data, which is a list of numbers, and this component actually creates new data. And then this is something that is doing something called a mapping. So it takes these numbers, a list of data, and it remaps it to from that group of data to from that list of data to a new list of data. And it does it just one by one. It takes the first one and makes some sort of operation with that. manipulation. In our case, it's a multiplication of each piece of data in the list. It takes it, multiplies it by 1.5, and then it puts it to a new list, and so on and so on. So when you have a Grasshopper definition, you can think of that definition a stream of data coming from one operation to another, and the data is being somehow transformed, changed in each of these components, in each of these boxes. Something happens to the data, and new set of data is being created with that operation that is happening there. That's not something that you would do in an imperative programming language, because there you would have to give the commands and repeat through, like iterate through the data manually using for loops and so on. That's basically what Anemone is doing in Grasshopper. It basically breaks the logic of functional programming, and it gives you an imperative set of loops. In other words, in an imperative programming language, what you care about are the commands that you actually schedule one after another. In a functional programming language, you care about the data, so it's data driven, and you just do some operations with the data, and what matters is the data. So you're just putting one piece of data from one place to another, and so on. How are you doing over there?
You asking me? Yeah.
Yeah.
I meanwhile program the example as well, so I can maybe just.
So can you paste the link to the Zoom?
Oh yes, absolutely.
And I will just share it, and maybe you can describe it.
Yes. Let's do this. I never tried this before, but hopefully it will work.
Sorry for not telling you before. It just came to my mind that we could.
Yeah, it's a nice surprise. No, let's share it like this. Embed code and link. Okay. Zoom.
There is a chat on somewhere.
Yes.
Okay.
Yes.
I got it.
It's in there.
Okay, it's Rust.
Yeah, I wanted to do JavaScript, but I just realized that if I was to type this fast, I might just as well use something that I'm more comfortable with currently.
So yeah. So the result is the same as mine, and maybe we can go through the code. I would just say that the first and the last line, let's forget it. That it's just something that tells the computer that this is what it should execute. So I think we can break down this a little bit.
So maybe you could even separate those two middle lines a bit. Yep, thanks. So Rust is. So today it is very modern for a programming language to be both functional and imperative at the same time. But similarly to what Jan did, I implemented this example in a functional style. So what happens there is that first we define it, the let res. Res is a name or shorthand for result. We define that that's the place the result is going to live in. Yep. And it's going to have a type. We haven't really talked about types, but
let's skip that. We just can say that this is some sort of a list, list of numbers.
It is pretty much that. So then we have a couple of commands chained with dots. So let's start to break it apart one by one. So the first part in parentheses is a range of numbers, and it's exactly as the sequence command in Grasshopper that Jan showed you, where the count there was configurable by a slider. So I just did the same thing only in code. I used constants there, so I decided this is going to be a constant sequence from 0 to 9, where 9 is the last element. But those values could actually have come from some inputs to the program.
We can say, just like here, there is the starting value, there is the step size, and there is the count. So we can do the same thing. We can say let s equals 0, we need to say that it's, we don't have to, actually, I don't think we need to specify the type like this.
Yes.
We can say let C equals 10. This is, the S equals 0, that's default here. C equals 10, that's something that I specified. And we could actually write something like this as C, right?
Yes.
So basically now what I have selected is basically the series. This is the starting number, this is the resulting number. And as a result, this gives us whatever is here. And also I will break it down a little. So I will say that series result equals SC. And if you don't mind, we will skip this part and I will place that here without explaining. So now at this point, well, what we are doing here is what we are doing here. So I will just do it like this, and I will make a group, which is, sorry, it's this one. So now this is the first part. Let's call it first part. 1. Now, this is going to be called 1. Now this will be the second part.
Yes, we can perhaps just call it series because then it's the same name. Isn't
All right. Well, but series is the operation that is doing that. I would say this is the operation.
Okay.
And this is the result, what comes out of here, like this series as a list. So let's do this. Let's call this one 2. And that's happening here.
Yes.
So, and this is written in 1 line. So that's cool.
Yes.
And then we have the interesting part, which is this. Can you explain that? I think this is the crucial thing and kind of difficult.
This is where we'll explore the similarities. So then there's the map operation, and in a way, what Jan did with the multiply operation in Grasshopper is that is a very specific baked-in version of the map operation. So the map operation actually takes multiple parameters. It takes something that it can produce values out of. So in our case, that is the series or the series result. So so that you can imagine as a sequence of values. So that is the first parameter for the map operation, and that is kind of implicit, and it's coded into the dot by which I separated the commands.
Sorry for interrupting you. I just realized that doing this in Rust, I think it's a better idea to multiply by 2. We don't have to do the typecasting here. It will be much nicer to explain. So I will just change it for you here.
I was just about to skip it, or I can even explain why that's necessary.
Let's not. No. Let's not even do that at all. So we have it like this.
Okay. Let's confuse people then.
Yes.
Okay, so then the important part about the map operation is that the other parameter it takes is another operation that it actually does on the data, on the values that are being produced. And in there, I wrote something that's called an anonymous function, and that is a function that takes one parameter which I named x, and returns that parameter multiplied by 2. I could have written there any other function that would transform the data and it would still be correct. So what the multiplication operation in Grasshopper is a specialized version of this, where you give it the parameters, or these are the numbers that you should multiply zipped together. And instead, what I did is I gave it the general operation that I can customize any way I want. And I just, in there, it just multiplies by 2. The product of that is still actually just a series of values, or in this concrete programming language, it's called an iterator. But you just can think about it, it can produce multiple values until you exhaust all the values, so the series ends. And that is something different than a list, and that's why the end there is this collect operation.
Maybe we don't have to discuss that because that's very just Rust. It's a Rust
kind of
thing.
specific. Yes.
Yeah. So yeah. No, what I would say, let's write a pseudocode, which is not in any programming language, but this will be a pseudocode. The computer can read it because it's not written in a programming language, but it should be easy for a human to read that. I would say result equals series. Take whatever comes out of series. Put it as an input into a map function. Map function means that take every single piece and iterate through a list of values, and for every single value do something. So here the map would be like this. Temporarily name values x. So temporarily, while I'm going through the list, I will call the values, I will give a name to each value. It will be called x, and with the value do something that is here. So this will be a function to apply on all x values.
Yes.
That's what we do here, and that's it. So basically you're saying take a list and with every single item of the list do this, and this function we can define somewhere else. So we can say that the function should be is x times 2.
Yeah, exactly. And this is actually exactly the meaning of functions in mathematics as well. There's no difference there.
Yeah. And surprisingly, even though this looks kind of exotic, could I ask you to write this in an imperative way with a loop? The same thing?
Sure.
Meanwhile, I will explain. Surprisingly, the same logic applies here with in Grasshopper. So we don't have the map function explicitly defined here, but it's somehow embedded in every single component of Grasshopper. So this multiplication, you can think of one specific implementation of a map function, a couple of map and a function multiplication, but in fact it works internally exactly the same way. So even multiplication is map that multiplies. Addition is map that adds. So if this was not x times 2, it would be actually this should be some sort of constant as well. Even here, multiplier. I should actually. Yeah, I've forgotten. So now this is a constant. This is this multiplier. Multiplication result is a mapping function that takes every single item in the list and multiplies it. And I'm specifying the function that should be used while mapping here, and I specify it somehow manually, which is a good thing because it can be anything. It could be, you can imagine that the data is not numbers, the data is geometry, and the function would be some sort of, I don't know, scaling or something. Like when we were talking about the parametric paradigm, or the first day when I was talking about different stages of computational design, there was this parametric picture that I was showing that for every single panel you make some sort of decision, you make the orientation, you make it more bumpy or everything. So basically that's a map function. I will take like proto panels, and for each one I will apply certain function, and I can, in a programming language, I can define the proto function here. The function that changes the proto panel to something else, and it can be something that is not this easy. It could be something that is huge, that like this can I can define it outside like this, and that can be a huge operation that you do. In Grasshopper, there all of these mapping functions are ready-made for you. So there is one ready-made for multiplication, there is another one ready-made for addition, there is another one that, for example, I don't know, scales. So even the scale is some sort of a mapping function where you input a lot of geometries and you apply certain function on that, and the function is scaling and so on. So this doesn't really apply only to numbers, but also all sorts of geometrical operations. I think we already have the imperative version of this, so we can see the difference. First we create, and I think when you know Grasshopper, this, even though it looks exotic as it's written, but this is a super easy way to think about processing data. And this suddenly starts to look a bit more weird. So let's explain this. This doesn't have an equivalent in Grasshopper. Maybe can you walk us through?
Yeah, sure. So for some people, this might actually be easier, and if you have no functional programming or Grasshopper background, this might actually make more sense for you. So the program is exactly the same, exactly equivalent. What it does is that first it creates the place that the result is going to live in. That is very similar to the last example. In this concrete example, the place starts out as an empty list, which we will slowly fill in with values. So that's what the for statement in the middle of the program is for. So once again, we iterate in this for loop over all the values between 0 and 10, excluding 10. And inside, well, we bind these values to the name of x, exactly as Jan was saying with the anonymous functions. Now, so you can imagine that this happens 10 times from 0 to 9. And each time it executes, x will have a different value. So it starts out as 0, then 1, then 2. And each time that happens, the code in the curly brackets in the middle is going to execute. And what that code does is that the list that we defined on the above line is going to get extended. A new value is going to be pushed at the end of the list. And that value is going to be equal to x times 2.
We can now discuss, should we, is this at least a bit clear? Is this explanation okay? Or are we going too much into detail?
Or too little into detail?
Maybe that. I just want to say that this is incredibly exciting for me because when we are programming, sometimes, you know, when we do some geometrical software, I first make a prototype in Grasshopper, which is super natural for me, very natural for me. And then we are trying to change it to a code. And sometimes for me, it's, I just naturally write everything in the functional way. Sometimes it's not a good idea, sometimes it is. But then it's incredibly exciting when I see that I can translate the Grasshopper thing almost one-to-one into a code, which is amazing. But I think I would really like to talk about two more concepts here. One is that, or two more facts. One is that with the functional programming, you somehow create a lot of data, and the same happens with Grasshopper. You first create the series, and it does exist. So all these numbers, they do exist. Then you do something with them, you map them, and another set of data exists. And the same more or less applies here. So we have the series, that's the first data that exists. Then we have the multiplication result, and that exists. So it occupies memory, which means that it's very memory demanding, and also allocating memory, using memory is very slow. So in a way, this potentially can be a very slow program, although the modern programming languages, they try to compensate for that, and sometimes it doesn't really matter. But you imagine that you're actually materializing data in memory. So this data exists, this data exists. Whereas here, you don't create the first set of data, you just have an X that lives only here in each iteration. It's shortly lived. Then you multiply it and place it into the memory. So it doesn't really exist anymore. So the original list of like these numbers. They don't remain anywhere. They are lost, and you just go and change the data as you go, and this doesn't occupy any memory. And it can be actually much faster. Yeah, okay.
Sorry, so what you said, that the data exists in memory, that is a very good way to think about it. And I think Grasshopper really does it that way. And it's a really good model to think about what's happening. But just to be like completely correct, the example in the Rust programming language you just did doesn't actually do that.
Yeah, no, I said it compensates for that.
Yeah, it compensates for that. So what it does is actually, it only creates the description of how it's going to get the data, which is way more efficient. But unless,
no, but
99% of the time, it is the same. It is equivalent. Only one is faster. So that's why it's a good model of thinking about things, that the data actually exists meanwhile.
Yeah. That being said, it means that if you're using a modern programming language, and using it in a functional way, it doesn't mean that you're making necessarily a slower program. Well, depends. Let's talk about one more concept, and that's the immutability. Maybe I can start. There is one. The important notion that you should take from this this presentation is that Grasshopper is a functional programming language. So let's not go too much into detail. In functional programming, you get something that is called higher order functions, and one of them is map. That's the one that we have, that basically takes certain amount of data, and as a result, it's the same amount of data. So it just changes every piece of data to something else. But if you have 100 input items, then you have 100 output items, and something happens with each of them. Then there is another function equivalent to this mapping, which is called reduce, which basically takes some amount of data and results in different amount of data, usually less data. In Grasshopper, we also have those. In a code, you basically define what should be the function that decides whether you keep or one piece of data or not. Now that's filtering. How to actually reduce the data. In Grasshopper, there is a nice example that I would like to show. So all of these are mapping functions. Reduction functions is, for example, mass addition. That's a super nice example that takes a list as an input and takes every single number and adds it adds one number to another, like all of them. That's an addition of all these numbers, and as a result, you've got one piece of data. So it reduced the amount of data, and it's just, I don't have 10 pieces of data, I just have one piece of data. So it reduced this. And then in code, there is the third higher order function, and it's filtering. And it basically takes some amount of data and outputs only some part of the data without changing it, but it makes some sort of evaluation. So for example, you can only output numbers that are higher than 5. So for example, so that function, the inline function here would be asking, is x larger than 5? And if the answer is true, then that specific x will be in the result. Otherwise, it will not be in the result. In Grasshopper, we don't really have filter functions like this.
You can create mask, right? Like
you can create a mask which is called a pattern here. So we can ask, is this number larger than 5? Which actually results in something that is called a pattern, true-false pattern, or in other words, a mask. So, but this still has 10 pieces of data. So this is still a mapping function. It creates the same amount of data, and then there is a function called cal pattern, and I can take these data and only keep those that were true that are true in this mask or pattern. And that cal is already, it's a reduction function, but these two together are a filtering function. So there is no filter in Grasshopper, but there is a combination of map and reduce. So, but this is also kind of interesting because unlike in a code where you create the mapping, filtering, and reduction functions yourself. You actually generate them or design them. Here in Grasshopper, you already have them as out of the box, but they still work the same. And I think knowing Grasshopper well actually is a good starting point to be a good programmer in the functional programming languages, which we have to say is still kind of rare and kind of it's considered to be a good skill, but then it can be incredibly useful at the same time.
Yeah, also it's just a good way to think about things.
And sometimes it can help you to solve problems in a very, very nice way. Let's talk about immutability. Just a little, and then we'll finish. We are much longer than we expected.
Yeah, as usual, I believe. Okay. Very, very short. So in functional programming languages, usually, and it's not 100% the case, everything is immutable, which means that let's take the Grasshopper example. So in the beginning, we have the series, which gives us this list of items, and that list exists all the time, and never anything is inserted into the list or removed from it or changed in it.
It's constant.
It's constant. It never changes. Even when we do the multiplication operation, what we get is another list, and the original one stays the same. And that is the principle or the thinking model behind it. While if you are allowed to mutate data, like I did in the second code example, what I started out was an empty list. And each iteration in the for loop, I added one item into the list, and my data actually changed. Like really quick side note, that's why I actually had to define the result variable as let mute, because I needed to tell the compiler that I will be changing this, which by default it doesn't allow you to do unless you tell it explicitly. So immutability is a very good way of avoiding bugs in your code. It has some drawbacks, mainly on the speed and performance side of things. But as a model of programming and thinking about problems, it is very powerful. You can do very easy parallelism with immutable data structures. So if the data never changes, or it can change in such a way that the other threads never notice it, you can parallelize a computation really easily, and that just works out of the box. So by usual, in usual, people would say that okay, so if I have things immutable, I have to copy them around. That's a okay way to think about it, but in practice, that is under the hood implemented in a way more efficient manner. There's special data structures that give you the impression that data is copied around, but internally data is reused way more. And,
which means that it doesn't necessarily always have to be slower.
Yeah, it likely will be still slower, but not as slow as it could be.
But at this point, I would really like to point out what I think makes Grasshopper so special and very, very, very good. What Grasshopper does right, and other similar programming languages or platforms or scripting tools get completely wrong. And I think that's what makes Grasshopper the main tool for computational design. One is that it's completely functional, and in a sense that we explain here, everything is either map or reduce function, slightly also filter, which is in an incredibly efficient way of thinking of geometry and data. And another thing is that immutability, which in practice actually means that you can reuse certain data. Just like I did here, you see that from this component, there are actually 4 wires coming out from one component. If this was mutable, which means like these components would change would change the data, that would mean that, okay, this one is changing the data to something else, and then also the output here would change, and we would have a lot of problems with some sort of concurrence, and like data would change without you knowing where does the change come from. And this is when Revit first had Dynamo as an option. I tried Dynamo. I don't know if it's still true, but at that point I decided Dynamo is not for me because it was not immutable. In other words, when you reference some geometry from the main Revit, it changed the geometry, and this is completely unthinkable with Grasshopper. It cannot happen that you reference some geometry from Rhino into Grasshopper and it changes the geometry in Rhino. This is the immutability. It doesn't change. So it generates new versions of the geometry, and when you decide this is the one that you want, you will just bake it or bring it somehow back to Rhino. And even inside of Grasshopper, it doesn't change. And this is not always the case, and this is not always the best thing for the purpose. I will give you an example when, well, the example of changing mutability is Dynamo, and maybe it has changed meanwhile, but the first version, it was changing the actual geometry, which is something that is a no-go for me. And then there is another example, and those are the performative visual programming languages, just like there is VVVV or there is Touch Designer, and there is something called Cables GL, which has awesome results. This is basically a visual programming language that lets you create all sorts of interesting 3D and 2D effects, even on websites. And actually, it's super powerful and it's well done. But the thing is that for our purposes as architects and designers, this is not suitable because you have the visual interface and it looks something like Grasshopper, but in fact you're stacking imperative commands one after another. And if you, in Grasshopper, it's super simple to understand that you're starting at the left and you're going to the right. So on the left, there are inputs, on the right, there are outputs, and the cables go from the left to the right. Here, it's not the case because you actually stack commands one after another, and sometimes you make an if statement, so you're bifurcating, you can take two paths, and then you go somewhere, and then you get loops, and you define that in this loop, repeat this thing over and over again, and you basically create something that is just a chain of commands rather than a chain of data being processed. And that's not so useful for us when the final result is some stabilized set of data. And that's what Grasshopper is also gets completely right. And I think these are the two secrets why Grasshopper is so successful and so widely used, and not all the other tools, because they got something like this wrong. And of course, there comes the simple user interface, there comes Rhino, that is super useful and very powerful on its own, even without Grasshopper. And there are so many reasons why Grasshopper is so successful, but technically, under the hood, I think it's the immutability and the fact that it's a functional programming language. Let's stop here, shall we? Is there anything that you would like to add?
No, I believe you said it all. Pretty much immutability really helps you program, takes away many of the things that could change under your feet. Unless you really need the performance, immutability is way simpler to think about. So
yeah,
I completely agree.
And in the modern programming languages, even that is usually not an issue, or not that much of an issue.
Yes.
Are there any comments? Was this at least a bit informative and understandable? Or anything that you would like to add or ask? I will open Facebook as well. And let's see if there is anything. I will stop sharing my screen. Yeah, I can. Do you want to say something?
Yeah, I can say something first. It's thank you for this presentation, and I'm curious. I have two questions. And when we start using another program, and I think our way thinking is changing. It's when we're modeling with lines in with solid surface or models. Now this way of making is transformed into syntax. And how did you adapt your way of thinking to traditional architecture practice?
Mainly, I was explaining this before, that the traditional practice, it never made sense to me. So for me, this was not a transition from something that is natural to something that is different. For me, it was finally finding something that is natural. And I believe that there are many people like this. Mainly in the generation when you know that how the digital actually works, you have all the experience with social media, internet, and all these things, and most of them, they work in certain way. And when you are ready to think in that way, then you also are ready to think in that way in your creative discipline. So for me, I didn't really make a transition. For me, it was a constant struggle not being in this paradigm. So making things in a conventional way, like drawing a house with a pencil and just looking for the best solution by hand, that I didn't know how to make decisions. And here I do know how to make decisions. So, and but I've experienced many, when I was teaching, I've experienced many students who maybe in their last year of studies, they first saw Grasshopper, and there's several kinds of people. Some people don't like it at all because, well, for obvious reasons, of course. No, not everybody has to like it. It is kind of difficult. It has slow results. You spend a lot of effort just trying to figure out the math and to put together a parametric model, and then it gives you some result, and the result is not exactly that you have, and you want to tweak one little part, and it's not really possible because you need to think in a systematic way. So of course it can be very frustrating, and that's completely understandable, and nobody is to be blamed for that. So it's not for everyone. Not because, well, because there are other good ways how to do things, and some people are ready to do it that way. Then there is another group of people who get very excited about the possibilities without actually knowing how to apply them in the practice. So it's just pure techno fetish. So just some people like it and start using it without knowing too much about the concepts behind, and they just experiment and they get results that they like. And later on, they figure out that it could be, there should be some sort of idea behind. So many people are trying to apply it to the conventional ideas, but then they're looking for ideas made especially for the computational paradigm, and then they become computational designers. And then there are very pragmatic people who understand immediately that this helps them to solve particular or partial problems in their conventional design. So for example, you can optimize solar gains or thermal losses, or you can optimize the number of elements or material that you have to use. So it's a very pragmatic reason why to use parametric design, and some people just use that as a partial, as part of their conventional design process. And again, this is completely okay to do it this way, because that's one of the reasons and intentions why this actually is even happening. Was that an answer to your question?
Yes, sure. Thank you. And I'm just curious about your opinion, and it's this question about that. And we was talk about blueprint, and I just remember Antoni Gaudi's works, and they are genius, and as far as today is concerned, and its work, they builders hasn't notations, but they did, and blueprint didn't exist then. And I'm just curious about that. Do you think that this systematic thinking and sometimes restrict our creation, or it can be similar works feature, and yes, I understand it's nice thing, and we produce different variation, and sometimes we are just thinking between 1 and 2, but it's computer doing so much variation when we are thinking, and I'm just curious about your opinion.
I think this is a broader question, and it's a very good one. I would define this as how much does the tool actually influence the result of what you do, and you cannot really avoid it. And it's not only the tool, it's also the notation, and it's also the building code, and it's also the standards. Let me complain a bit at the beginning. I think that right now, worldwide, what happened is that the modernist movement, it somehow got standardized. And when they were starting, when there was Le Corbusier, all these modernists, Bauhaus, Cian, when they were talking about stuff, they were avant-garde. That was something that was not usual. They were the ones who were saying we are the progressives, just like we are now saying that we are the progressives. And they were not the majority either. But somehow what they were saying, it became prevalent, it became a standard. So now when we have a building code, when you want your building to actually be built and somebody is approving it, a politician or a clerk or some officials, when they're looking at your plans, they go according to standards and building code. That is basically the modernist way of thinking. So also this completely influences your creation. So everybody who wants their house to be built, they need to comply, they need to follow the modernist rules, or at least they need to somehow explain it in the modernist terms. Like, for example, you need to, there is very often here, there is a code about the shape of the roof. And if you think about all the crazy buildings that are now possible, you wouldn't even be able to identify what the roof is. And that's an example. So as much as the building code is completely influencing what you can do and what you're doing, the tools are completely influencing what you're doing, and also the way of thinking, the paradigm, what the computers offer you to do, you cannot avoid it. It's the tool and how much you can actually tweak the tool. And also the tool opens new questions, and also the environment where you are, it's shaping what you can actually do. And I think this is not a new thing. Very often people are saying, okay, so when something is built or rendered, they say, okay, this is Maya, this is Grasshopper, this is, I don't know, Houdini. But at the same time, when I'm walking on the street, I can say this house was designed in SketchUp, because I can see that, because it influences what you do. And the same applies for in history. You see that when there are some vaults or cupolas, it was a new thing that it's possible to build a cupola on top of a rectangular or square floor plan or like footprint. That was a new thing. And it's a completely technological thing. Just like now in Grasshopper, we can do crazy shapes. In Baroque, or I don't know, I think it was Baroque, they were out of sudden able to construct a cupola, a hemisphere on top of a square, which was a new thing. And then they had a compass, and they could draw perfect circles. And they started to use the compass excessively in Baroque. Again, a tool that completely influences what you're doing. And it's not only that you can, therefore you should, but that also opens new questions, like new topics in creative discipline. It tells you like, okay, now we have this, and how can it move our thinking a little bit further? Yeah, a comment from the chat. I have the same thought in ArchiCAD from the stairs railing. Yeah, you can actually see what a building was designed in. And if the tool is sophisticated, then cool. If it's Maya, wonderful. If it's Rhino and Grasshopper, wonderful. If it's SketchUp, not so much. All right, anything else? Shall we finish here?
Thank
Okay.
you.